All right, hello everybody. Welcome to the first part of the video for section 2.2 now, continuing on with our study of linear functions. And here we'll be focusing in on graphs of linear functions and some of the properties of those graphs and different features. Okay. All right, so when we talk about graphing linear functions, there are three primary approaches we can take. Okay. So the first one, which is probably the second most used one, which would be by plotting points. So at least 2 points on the line. If you plot them, then you can go ahead and connect them. That's one of the nice things about lines is really you only need 2 points to figure out what shape a line should take. The second method here is the one that we probably use the most, which is using the initial value or the starting value. Or recall that that's also in the, in the f of x equals mx plus b equation. The initial value would be that value for b there. And that's also, remember, the output when x equals 0. So we use that together with the rate of change to make the graph. And I would say, again, that is the most common method used for graphing a line. And then the last one, which would be the least common, but since we took some time studying transformations in chapter 1, we should at least be aware of it, and that's using transformations, the identity function f of x equals x. So recall that f of x equals x is one of our toolkit functions called the identity function, and so we can do transformations of that to get any line that we want. All right, so let's look at using each of these. So if we're going to graph a function using 2 points, well, here we are given the points -2, 3, and 6, -7 on the line. So we can go ahead and graph those. So -2, 3 means if we started at the origin, we go to the left 2 and up 3. Get a point there. And then 6, -7 means go over 6. So 2, 4, 6, and down 7, 2, 4, 6, 7 to here. Okay, then we can connect the dots there through the 2 points. Of course, since these lines go on forever and ever, we can connect them or put arrows on them to show that. And there we go. That would be our line. Okay, and again, you could do more points on the line if you wanted to, but 2 is just enough. All right. Okay, our second method now, using the initial value together with the slope. And I think that we've actually done this already in one of our prereq practices. But just as a review, so again, we have our function here, f of x equals 2/3 x plus 3. That lines up with our form f of x equals mx plus b. And lining those up, we see the value of b here is 3. The value of m is 2/3. We call that value b, that's our vertical intercept. So that tells us where the line intercepts the vertical axis. So we can go up to that point right here and put a dot. And recall that also the coordinates of that right there are always going to be 0, b. So in this case, it'd be 0, 3, since our value for b is 3. And then we can use our slope, that 2/3, by recalling that another way to think about slope is rise over run, right? So starting from the vertical intercept that we have marked, we can use rise over run, meaning going up 2 and over 3. So rising 2 and running 3 to make another point. So we could go from here up 2 over to 3, and we'd get another point right about here. And that now gives us 2 points, and so we could connect those to get the graph of our line. However, it can be helpful to draw more points, so we can actually keep going, go up 2 and over 3 again, and get another point here. Go up 2 and over 3 to another one here. From that vertical intercept, we could also go down 2 over 3, down 2 over 3, down 2 over 3, kind of doing the opposite, and you can see our lines start to trace out there. Okay. And then just as before, we can connect those dots through all of the points there. And again, of course, put in our arrows, and there is the equation of our lines. Or sorry, the graph of our line. Okay, last one now, which is a little more involved, and like I said, probably the least common way that we will, or least used way we will graph the equations of lines, is by doing transformations of the identity function f of x equals x. Okay, and we're going to graph this function. I'm going to write it off to the side here so I don't forget it. So g of x equals -1/2 x plus 1. I'm going to switch my window here to Desmos. Okay, so notice here, I've got the this red line here is the function, sorry about that, is the function f of x equals x, so that's our identity function. So we know it goes through the point 0, 0. It's got a slope of 1, so this is the correct function. And we're going to graph from the previous slide, g of x equals -1/2 x plus 1. In order to graph that here, we need to think about what transformations have taken place in order to go from this function, -1/2 x plus 1, to this one, f of x equals x. Okay? And I see 3 primary transformations. I see a negative sign here. I see a 1/2 on the outside of the x that does something. And then this plus 1. Okay? So let's think about what each of those do. First, the negative sign. Or actually, sorry, before I do that, I should also point out the way my animation is set up here. So we've got f of x equals mx plus b. Note down below right now, b is equal to 0 and m is equal to 1. So this is really like 1 times x plus 0 right now. 1 times x is x. X plus 0 is still just x. So right now our equation is f of x equals x. That's what we see graphed. Okay, so we're going to make the m value then 1, or -1, since it's negative down below. And recall, how is that going to change the graph of the function? All right, it's going to reflect it across the horizontal axis because it's a negative sign on the outside. So it's going to cause a vertical reflection, which means across the negative axis. So let's watch that. And it looks like that happened. Okay. Then next we're going to think about, what does this 1/2 here do? Okay, well, again, it's a 1/2 on the outside of the variable, which means it's going to impact the outputs, which means since the 1/2 it's going to do on the outside, it's going to do exactly what we think it'll do. So 1/2 is going to do a compression, a vertical compression by a factor of 1/2. So let me go back to this. Actually going to do a slider here. And notice if you watch the outputs, they're all going to get pushed towards the center because they're going to have a compression. So as I slide this over to -0.5, notice that it gets compressed. If I go back to -1, again, slide over to -0.5, we see things are compressed from the top and the bottom. And then finally, this +1 here. Okay, that's a 1 being added on the outside. So that's going to be a vertical shift up 1 unit. And if I slide my value for b here over to 1, oops, I went too far. You see it went up. So let me do it again. Back to 0, slide up to 1 somewhere. There we go. We see it went up. So this now, this new red line that I've drawn, okay, this will be the function g of x equals -1/2 x plus 1. Okay, and as I said, this is the least common way to graph the equation of a line. So we could also see how we could have used the most common way to do this, right? So we see a +1 is our vertical intercept. So we have a vertical intercept there. And the -1/2, since it's negative, tells us to rise -1, which means go down 1, and then run 2. And we see if we do that from our vertical intercept, we end up at this point here, which is on our line. Go down 1/2 again, we're still in the line, down 1/2, down 1/2. So you see that we do in fact get the same line if we connect all those dots. Okay. All right, that's all for now. Thank you for watching.